in this session we solve few problems related to the waveguides. So, we will take two problems which are based on parallel plane waveguide, and then we will take two problems which are based on the rectangular waveguide. Let us consider a problem here that in a parallel plate waveguide the phase velocity of TE3 mode is 1.4 c, where c is the velocity of light. Find the guided wavelength of TM2 mode inside the waveguide. The waveguide has been filled with a material having dielectric constant of 9 and the frequency of the wave is 1 gigahertz. So, in this case we are given the velocity of TE3 mode, and as we know the velocity is related to the size of the waveguide. We can find out from this information what is the size of the waveguide, and once we know size of the waveguide, then we can find out the phase velocity for any other mode. So, in this case for TM2 mode, and once we know the phase velocity and the frequency, then we can find out the guided wavelength for this mode, which is TM2 mode. So, as we know the phase velocity for any mode Vp is given as omega by beta, where beta is the phase constant in the direction of wave propagation inside the waveguide, and that is equal to the velocity of light in the medium which is filling the waveguide divided by 1 minus m lambda divided by 2d whole square, where lambda is the wavelength and v is the velocity filling the medium. So, this velocity in this case, since the waveguide is filled with air, this v is c. So, we have essentially the information of this velocity which is 1.4 c, and then we have the information which is this one which is c. So, now if I substitute these quantities into this relation, first of all this velocity, now since the dielectric constant of the material which is filling the waveguide is 9, this velocity v will be equal to the velocity of light c divided by square root of epsilon r, which is 9. So, that is equal to c upon 3. Then by inverting this relation, we can get this quantity here which is m lambda upon 2d, that will be equal to square root of 1 minus v divided by Vp, that is equal to square root of 1 minus c upon 3, this velocity divided by 1.4 c. So, solving this, essentially we get this quantity here, and in this case this velocity is given for the mode which is TE3 mode. So, m is equal to 3. So, for TE3 mode, m is equal to 3. So, you can substitute here. So, we get 3 lambda upon 2d, that is equal to square root of this quantity which is 1 minus 1 upon 4.2, that will be equal to 0.58. So, from here we can find out this quantity lambda upon d. So, we get lambda upon d, that is equal to 2 into 0.58 upon 3. Now, once we know this quantity lambda upon d, then we can find out the phase velocity for TM2 mode. So, the phase velocity for TM2 mode is the Vp will be equal to V divided by square root of 1 minus, since now in this case m is equal to 2. So, this will be 2 upon lambda upon 2d whole square. So, we can substitute for this lambda upon d into this expression from here. So, this is 2 will cancel. So, this will be equal to the V divided by square root of 1 minus this quantity, which is 1.16 divided by 3 whole square. And V is nothing but the velocity of light in that medium which is filling the waveguide. So, this is nothing but c by 3. So, this is equal to c by 3, which is c is 3 into 10 to the power 8 meters per second. So, this quantity V here is equal to 3 into 10 to the power 8 divided by 3, that is equal to 10 to the power 8 meters per second. So, substituting here for V, we get 10 power 8 divided by this quantity 1 minus 1.16 upon 3 whole square, that will be equal to 1.229 into 10 to the power 8 meters per second. Once we know this velocity, phase velocity and the frequency, then we can find out the guided wavelength of this. So, lambda g for this will be equal to Vp divided by the frequency, which is 1 gigahertz. So, 1 gigahertz. So, this is equal to 1.229 into 10 to the power 8 divided by 1 gigahertz, which is 10 to the power 9. So, that gives us 0.122 meters. So, in this problem, the characteristics for a particular mode are given, which is a TE3 mode, and we are asked to find out the properties or the characteristics for TM2 mode. And since these are related through the size of the waveguide and the frequency, essentially we can find out from here the characteristics of TM2 mode after getting the dimension of the waveguide. That is what precisely we have done in this. Let us consider another problem, which is again a problem on parallel plane waveguide, but this waveguide now is divided into two parts. So, essentially we are having here parallel planes which are given like this, and the half the waveguide is filled with one dielectric material and half the waveguide is left empty. So, the problem here is as follows: in the following waveguide, find the frequency at which the TE1 mode does not have any reflection at the waveguide junction at z equal to 0. So, we have here the parallel plane waveguide, this is z equal to 0. So, for z less than 0, the waveguide is filled with a material with the dielectric constant 4 and relative permeability 10, and for z greater than 0, the dielectric constant is 1 and the relative permeability is 1, and the width of the waveguide or height of the waveguide is equal to 10 centimeter. So, now we have to find out a frequency for which there will not be any reflection from here. What that means is essentially we have a travelling wave which is coming here in TE1 mode, and since there is no reflection, in this region also we have only forward travelling wave, in this region also we have only forward travelling wave. So, the problem essentially can be solved by matching the boundary condition at z equal to 0 for the mode which is in this region for z less than 0 and for the region which is z greater than 0. So, first we get the fields for TE1 mode and essentially match the boundary conditions. Now, as we know, for TE1 mode we get the field components which will be the y component, which will be like this, y direction is coming out of the paper. So, we have the y component for the electric field, and for the magnetic field we will have a z component and the x component. So, for matching the boundary condition, then the y component, which is this, it should be continuous across the boundary, and also since we are normal component of the magnetic field, that should be a continuous. So, we can essentially apply the continuity of the z component of magnetic field and the y component of the electric field for the mode. So, at z equal to 0, we have got E y1 is equal to E y2 and H z1 is equal to H z2. Now, the modal fields will have different phase constants in z direction, because now the medium which is filling the waveguide is different for z less than 0 and greater than 0. So, let us say that the phase constant in this is given by beta z1 and the phase constant in this is given by beta z2. This is the phase constant for T1 mode in this region and in this region. Let us call this as 1. Okay, we call this region as 1 and this is 2. So, now we can write down the field expressions here. So, we know the field expression, if I write down at z equal to 0, we will get this will correspond to some E0 1 sine of pi x upon d, that will be equal to A02 sine of pi x upon d, which essentially will give that the amplitude of these two E01 is equal to E02. That you get from the continuity of the y component. For the z component, we know this is E01 upon eta 1 beta z1 upon beta 1, where beta 1 is the phase constant in a medium which is filling this waveguide for z equal to z less than 0. So, if I take a medium which is of infinite extent and whose dielectric constant is 4 and relative permeability is 10, then beta 1 will be the phase constant of uniform plane wave in that medium, that multiplied by sine of pi x by d, that will be equal to E02 upon eta 2 beta z2 upon beta 2 sine of pi x by d. So, this equation we are getting from here, this comes from here, and this equation is coming from the magnetic fields from here. So, from the first equation we have got E01 equal to E02. So, this will cancel, and this sine pi x by d, that is again common on both sides. So, we get from this boundary condition beta z1 upon eta 1 beta 1, that is equal to beta z2 upon eta 2 beta 2. We can write down for beta 1 and eta 1. So, from here we get, by substituting the medium parameters, we get beta 1 eta 1 equal to omega square root mu 0 mu r1 epsilon 0 epsilon r1 into eta 1, which is square root of mu 0 mu r1 divided by epsilon 0 epsilon r1. So, we get from here this will be omega mu 0 mu r1. Similarly, we can calculate this quantity here, which is beta 2 eta 2, that will be, since this medium the relative permittivity is 1, relative permeability is 1, essentially this quantity, if you substitute mu r equal to 1 epsilon r equal to 1, we will get beta 2 eta 2, that will be nothing but omega mu 0. So, substituting now for these two in this expression, essentially we get omega mu 0 beta z1 is equal to omega mu 0 mu r1 beta z2. Again mu 0 omega will cancel on these two, and this quantity now we can write down in terms of the phase constant of the medium beta 1 and the phase constant of the medium beta 2. So, from here we can get square root of beta 1 square minus pi upon d whole square. General we have here m pi upon d, but since we are talking about a mode which is TE1 mode, that is what is incident on this. So, you put m equal to 1, that will be equal to mu r1 square root of beta 2 square minus pi upon d whole square. Keep in mind, we are essentially assuming here, keep in mind that the T1 mode which is coming here, on this side also only the T1 mode propagates. It is possible in general that many other modes might propagate in this region. However, we are saying that since the field variation in this has to be identical to the field variation which is going to get excited in this, for matching the boundary condition, continuity of the electric field, the field distribution in this region must be identical in the transverse direction to the field distribution in region 1, and that is the reason we are saying that the mode which is going to propagate in this will also be T1 mode, and that is why the index for this also will be equal to 1. Once we get that, then we can simplify these expressions, and we get from here beta 1 square minus pi upon d whole square, that is equal to mu r1 square into beta 2 square minus pi upon d whole square. So, from here we can get beta 1 square minus mu r1 square beta 2 square, that will be equal to pi upon d whole square into mu r1 square minus 1 with a minus sign. Now, noting that this quantity here beta 1 is equal to omega square mu 1 epsilon 1, that is omega square mu 0 mu r1 epsilon 0 epsilon r1, and beta 2 square is equal to omega square mu 0 epsilon 0. We can substitute into this expression here, and from here we can find out this quantity omega, which will be equal to pi upon d square root of 1 minus mu r1 square upon mu 0 mu r1 epsilon 0 epsilon r1 minus mu r1. So, this is the frequency at which we have a continuity of the field, and therefore, we will not have any reflection from this boundary here, which is at z equal to 0. So, even if the medium properties inside the waveguide suddenly change from these parameters to free space, still there will not be any reflection from this discontinuity, and wave will be launched inside this waveguide without any reflection. So, this is the frequency at which essentially the wave can be launched without any reflection, even if we are having a medium discontinuity inside the waveguide. Substituting now for these parameters mu r1 equal to 10, epsilon r1 equal to 4, and all that, we can solve for the frequency. So, this omega will be 2 pi into frequency. So, we can calculate from here the frequency that will be equal to 1.927 gigahertz. In fact, as we have seen for parallel plane waveguide analysis, that the modal propagation can also be seen as the reflection of the uniform plane wave on these conducting planes. So, we can visualize this TE1 mode as if the plane wave is going like that, reflected between these two planes, and we have a sustained propagation. Then we know that this plane wave essentially is going to see this dielectric boundary, and we know that there is no reflection for a uniform plane wave from a dielectric boundary when the wave is launched at the Brewster angle. So, for this, if I can visualize this TE1 mode as superposition of the uniform plane waves, then I can find out an angle at which the wave is incident at the Brewster angle at this interface, and then from there I can calculate the frequency for which we will get no reflection from the boundary. So, this problem can be solved in fact in two ways. One is taking the fields for a particular mode and then matching the boundary conditions at z equal to 0. Second way is that visualizing this TE1 field by superposition of uniform plane waves and then applying the concept of Brewster angle. And both the methods are acceptable, and both the methods essentially give the same value. Let us now consider a problem which is based on rectangular waveguide. Let us consider a rectangular waveguide of cross section 4 centimeter into 3 centimeter cross section, and that carries the dominant mode, and as we know the dominant mode of a waveguide is TE10 mode. The frequency of the mode is 6 gigahertz. The maximum peak electric field measured inside the waveguide is 50 volts per meter. Find the expression for the electric and magnetic fields inside the waveguide and the power carried out by the waveguide. So, first you have to find out the field expressions. Once you know the field expressions, then we can find out what is the Poynting vector. Once we get the Poynting vector, we can integrate the Poynting vector over the cross section of the waveguide, and then we can get the total power carried by the waveguide. So, problem essentially first is to find out the fields given the condition that the maximum electric field is 50 volts per meter, and then find out the Poynting vector and then the power carried by the mode. So, in this problem the waveguide is a rectangular waveguide. So, A in this case is 4 centimeter. So, writing in meters, this is 0.04 meters, and B for this is 0.03 meters, and the mode which is the dominant mode for the waveguide that is TE10 mode. So, for this waveguide H, the parameter which you have defined for the waveguide, that is nothing but pi upon a. So, it is equal to pi upon 0.04. Once we know this, then we can find out what is the phase constant for this mode on this waveguide. So, that is beta, that will be equal to square root of omega square mu epsilon minus pi upon a whole square. The waveguide is filled with air. Nothing has been given about what material is filling the waveguide. So, we assume that waveguide is filled with air. So, the relative permeability and relative permittivity for the media, for this medium filling the waveguide, are unity, and the frequency is 6 gigahertz. So, we can write here omega will be equal to 2 pi into 6 gigahertz. So, 6 into 10 to the power 9 radians per second. Mu is equal to mu 0, which is equal to 4 pi into 10 to the power minus 7 Henry per meter, and epsilon will be equal to epsilon 0, which is 1 upon 36 pi into 10 to the power minus 9 Farad per meter, and pi upon a is given here. So, if I substitute all these values inside in this expression, we get the phase constant for this mode beta, that is equal to 98.09 radians per meter. Now, if I look at the expression which are given for the T10 mode inside this waveguide, we have got the expressions that Hz is equal to d, where d is some constant, cos of pi x upon a, Ey, that is equal to minus j omega mu divided by pi upon a d into sine of pi upon a into sine of pi x by a, and Hx is equal to j beta upon pi upon a d into pi upon a sine of pi x upon a, and the other field components for T10 mode are 0. So, now what we see here, that this is the constant in terms of which we had derived all the field components. So, Ey was in terms of d, Ex was in terms of d. However, now this parameter d is not given. What is given is the maximum electric field, the peak electric field, which we can measure inside the waveguide, is 50 volts per meter. That means this quantity, which is the coefficient of this, that quantity is 50 volts per meter. So, essentially what this will cancel. So, what that essentially means is that the peak electric field that is equal to omega mu into d, that is equal to 50 volts per meter. Since I know the frequency, I know the permeability, which is free space permeability, I can find out the value of d, which is 50 divided by omega mu. So, this is 50 divided by 2 pi into 10 to the power 9 into 6 gigahertz multiplied by 4 pi into 10 to the power minus 7. That will be equal to 1.055 into 10 to the power minus 3. So, once I get the value of D, then I can substitute into these expressions and I can find out the field components. So, I get now the field components E y, that is equal to minus j 50 sine of pi x upon 0.04 h x will be equal to j 0.1035 sine of pi x upon 0.04 and h z will be equal to 1.055 into 10 to the power minus 3 cos of pi x upon 0.04. So, I have substituted the value of D in these three expressions. In fact, from here this is the magnetic field. So, that dimension of D should be amperes per meter. So, this is now the fields which we get for this waveguide for the dominant mode, and once we know this field, then we can write down the Poynting vector. So, we have got Poynting vector P, that is equal to half a real part of E cross H conjugate. So, this one S z and E y, they will not have any real part because this is having j, this does not have j. So, product of these two will give the power which will be imaginary. So, this essentially would be equal to half into E y into H x. So, this is 50 into 0.1035 into sine square pi x upon a. Once I know this Poynting vector, then I can find out the total power carried by the waveguide W, that will be equal to the integrated Poynting vector over the cross section. So, x will be 0 to a, y is equal to 0 to b, Poynting vector dx dy. So, I can substitute for p inside this and put a and b, you will get the total power carried by the waveguide W, that will be, if you solve this, you will get 2.588. So, you get 2.588. The Poynting vector does not vary in y direction. So, this integral with respect to y will be simply b. So, that will be equal to b integral 0 to a sine square pi x upon a into dx. So, substituting now, solving this and substituting the values for a and b, we get here 2.588 b multiplied by integral of this is a by 2. So, that gives us 1.55 into 10 to the power minus 3 watts. So, the power carried by the waveguide is 1.55 milliwatts. So, see what we have done in this problem. In this problem, the waveguide cross section was given, the frequency of operation is given, and the maximum peak electric field is given, and then from here we are supposed to find out what is the power flow inside the waveguide. So, first we calculate from here the fields, and in this for T10 mode, for dominant mode, the fields are having component which is Ey, Hx and Hz. So, we calculate the field components which is Ey, Hx and Hz. Put a constraint that the peak amplitude for the electric field is 50 volts per meter. From there we calculate this unknown parameter D. Once we get D, we substitute into the expressions and we get the three components of the fields, and then we calculate the Poynting vector, which is nothing but Ey multiplied by Hx, and then we integrate the Poynting vector to get the total power carried by the waveguide. Let us take one more problem here, that is a rectangular waveguide made of copper has 4 centimeter into 7 centimeter cross section. The waveguide is filled with a material with dielectric constant 3, and this dielectric material is lossy, so it has a loss tangent of 10 to the power minus 5. Determine all the modes which will propagate at 3 gigahertz. What is the total attenuation of the waveguide in dBs per meter for the dominant mode? The conductivity of copper is 5.88 into 10 to the power 7 mhos per meter. So, in this case there are 3 things we have to find out. First, we have to find out all the modes which will propagate inside the waveguide at 3 gigahertz. Second, the attenuation constant of the waveguide, which will come from 2 components. One is because of the lossy dielectric, because it has a loss tangent of 10 to the power minus 5, and the finite conductivity of the walls, because here the conductivity is not infinite. So, there will be conductor losses in the waveguide walls. So, we have to calculate the attenuation constant for the dominant mode of the waveguide. So, let us see how do we proceed for this. Firstly, to find out how many modes will propagate at a given frequency, we essentially find out the cutoff frequency, and then we find, then if the cutoff frequency is less than the frequency of operation, then the mode will propagate. If the cutoff frequency is higher than 3 gigahertz, then the mode will not propagate. So, we know for a rectangular waveguide, the cutoff frequency f of c, that is equal to 1 upon 2 pi square root mu 0 epsilon 0 epsilon r, the dielectric material we are talking about. So, the relative permeability is equal to 1. Also, since the loss tangent is very small, for calculation of cutoff frequency, we consider the dielectric constant almost real, and that is equal to 3. So, the epsilon r is equal to 3 multiplied by m pi by a whole square plus n pi by b whole square the power half. That is the expression for the cutoff frequency, and we know this quantity 1 upon square root mu 0 epsilon 0 is nothing but the velocity of light in vacuum. So, 1 upon square root mu 0 epsilon 0 is equal to 3 into 10 to the power 8 meters per second. Substituting this, we get f of c, the cutoff frequency of a mode, that is, this will be, this divided by 2 will give me 1.5 into 10 to the power 8 divided by square root of epsilon r, which is square root of 3. this m pi will cancel with this pi. So, this will give m upon A, which is for this waveguide is 7 centimeter and B is 4 centimeter. So, this will be 0.07 whole square plus n upon 0.04 whole square root. So, simplifying this, we get essentially 1.5 into 10 to the power 8 divided by root 3 into 100 into m upon 7 whole square plus n upon 4 whole square root. This will be 100 square here. So, from here essentially we get the condition for m and n. So, if m square upon 49 plus n square upon 16, if the frequency f c is less than the frequency which is 3 gigahertz, then the mode will propagate. So, what that means is, if this quantity here, if I substitute here for the frequency, then we get that if this quantity is less than 3 upon 25, then the modes will propagate. So, now we can try for different values of m and n, and as we know m and n both are integers. So, we can start with all possible combinations of m and n for which this condition is satisfied. So, we can take m is equal to 1, n equal to 0, we can take m equal to 0, n equal to 1, we can take m equal to 1, n equal to 1, we can take m equal to 2, n equal to 0, and beyond this, this condition will not be satisfied. So, essentially we got the modes which would be corresponding to Te or Tm with the indices for m which is going from 0, 1, 2 and the second index which is going from 0 and 1. Now, as we know for Te case, one of the indices non-zero will still give me the mode, whereas for the transverse magnetic case both the indices have to be non-zero. So, the modes which will propagate inside the waveguide are corresponding to this. You have Te 10, then you have Te 01, then you have Te 11, but for both the indices non-zero, even the Tm mode will be existing. So, you have got Tm 11, and then for here again you will get Te 20. So, at 3 gigahertz inside this waveguide, these 5 modes will propagate: Te10, Te01, Te11, Tm11 and Te20. The second part which is asked in this problem is to find now the attenuation constant for the dominant mode, and that is the Te10 mode. Since the loss is coming from two components, one is dielectric loss, other one is the conductor loss, and since the losses are small, what we do is we calculate these losses one at a time, and then we calculate total attenuation constant, which will be sum of the two attenuation constants. So, first we calculate beta for the Te10 mode, and that is square root of omega square mu 0 epsilon 0 epsilon r minus pi upon a whole square. If I substitute the values for epsilon r, which is 3, and a, which is the dimension of the waveguide, that is 7 centimeter, so it is 0.07, I get the propagation constant, which is 99.14 radians per meter. Now, the attenuation constant due to dielectric loss, as we have derived, alpha d, that is equal to omega square mu epsilon 0 upon 2 beta into tangent of delta, tan delta. So, I can substitute here, which is 2 pi into frequency square and this quantity here mu into epsilon 0, that will be 1 upon velocity square. So, this will be 3 into 10 to the power 8 square into 2 beta into tan delta, which is 10 to the power minus 5. This is what is given here, that the medium has a loss tangent of 10 to the power minus 5. So, I can substitute these values for all this, and then I can solve for alpha d, which will be equal to 5.94 into 10 to the power minus 3 Nepers per meter. Then we can calculate the conductor loss, the attenuation constant due to the finite conductivity of the walls, and that, as we know, is given as the surface resistance into 1 plus 2b upon a fc upon f whole square divided by eta b square root of 1 minus fc upon f whole square, and fc we know is the cutoff frequency for the TE10 mode, which is nothing but 1 upon 2a square root mu epsilon, and in this case it is mu 0 epsilon 0. So, that will be equal to 1.237 gigahertz, and the surface resistance is square root of omega mu upon 2 sigma. So, I can substitute the value of the conductivity for copper, which is 5.88 10 to the power 7. I know the frequency, which is 3 gigahertz. So, I can calculate this quantity, which is the surface impedance. I can substitute into this. So, we have all the parameters. We know the cutoff frequency, we know the frequency of operation, we know the dimension of the waveguide A and B, we know the surface impedance, and we know the eta, which is intrinsic impedance, which is 120 pi for the free space. So, by substituting these values, essentially we can calculate this quantity alpha c, which is equal to 0.438 into 10 to the power minus 3 Nepers per meter. Then, since the losses are small, the total attenuation constant alpha is approximately equal to alpha d plus alpha c, and that will be equal to the attenuation because of dielectric, which is 5.94. So, 5.94 into 10 to the power minus 3 plus 0.438 into 10 to the power minus 3 Nepers per meter. So, we can add this and you find out the total attenuation constant for this waveguide. Then this attenuation constant now is in Nepers per meter. If I multiply this quantity by 8.68, I will get the attenuation constant in dBs per meter. So, essentially see what we have done in this problem. Firstly, though, we were asked to find out how many modes will propagate inside this waveguide. So, at a given frequency, the dimension of the waveguide are given, the dielectric constant of the medium filling the waveguide is given, and we are asked to find out how many modes will propagate. So, first we find out the cutoff frequency for modes, then you find out a condition for m and n for which the cutoff frequency will be less than the frequency of operation, which is 3 gigahertz. So, we get this condition. From here then you find out what are the indices which can satisfy this condition, and then by using the knowledge that TE modes can exist even when one of the indices is not 0, whereas for TM mode both the indices have to be non-zero, we find these modes which can propagate inside this waveguide. From here then we calculate the, for T10 we can calculate the phase constant, then by using the expression which we have derived we find out the attenuation constant due to dielectric, and then we find out the attenuation constant due to the finite conductivity of the waveguide walls, and the sum of the two essentially gives the total attenuation constant. So, these are some of the representative examples which you will see for the waveguide. Typically the waveguide dimensions are given, the frequency of operation is given, and we have to find out the modal characteristics of the waveguide, that is how many modes will propagate. And also we have the problems where we have a dominant mode which is propagating on the waveguide, and then we would be interested in finding out how much power will flow, what will be the field expressions for that mode, what will be the Poynting vector, what will be the loss, and so on. So, this once we see these problems, then on the similar lines other problems related to the waveguide also can be solved very easily.